Everyone, in this video we're going to talk about the fundamental theorem of algebra. And we look at the top of the screen and what we see are four different equations. And these four equations, we want to take a note of the degree of the equation. And what we mean by the degree is the highest exponent that we see. So for equation number one, we see 2x minus 1. And notice we don't see an exponent on our x variable, so we would say it's 1. So its degree is 1. And look, it has one solution. The next one, we have a degree of a 2, and we have two solutions. We have a degree of 3, we have 3 solutions, and we also see another degree of 3 and we have 3 solutions. So hopefully you're noticing a pattern here, and this is what the fundamental theorem of algebra states. It says if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. So we take that theorem and we can find a corollary off of that theorem that states if f of x is a polynomial of degree n where n is greater than 0, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated twice is counted as 2 solutions, each solution repeated 3 times is counted as 3 solutions, and so on. So the fundamental theorem of algebra states or tells us that if I'm looking at a polynomial and it has a degree, whatever the highest degree is, as long as it's greater than 0, then that's the number of solutions that my polynomial equation is going to have. And that's really helpful because when we're looking at a polynomial equation, we can look at it automatically and say, hey, there's going to be this number of solutions because we can identify the degree, and if we can identify the degree, we can identify the number of solutions. So let's look at two different examples here. The first one, we're just going to figure out, hey, how many solutions are there? And then the second example is going to be a little bit more involved. We're going to use our synthetic division process, our rational root theorem, to actually figure out what our zeros are. So on these two examples, we see it says how many solutions does the equation have? So for number one, we see x to the fourth minus 2x cubed plus 5x plus 12 equals 0. And notice that my degree would be a 4. So this one has 4 solutions. Number two, f of x equals x cubed minus 6x plus 21. Our degree is a 3. So this one would have 3 solutions. Okay, so pretty easy on those examples, because we're not actually finding what the solutions are. We're just stating, hey, since the degree is this, there are that many solutions, okay? Now, our last example that we're gonna do, we're actually gonna find these zeros now. So before we do that, let's identify how many zeros we're actually trying to find. So we see x to the 5th plus 3x to the 4th plus 9x cubed plus 23x squared minus 36. So I noticed that my degree is a 5, so we're looking for 5 solutions here. And so once we're looking for our solutions, we need to be careful and make sure we look for any repeated solutions as we're going. So let's start off now and let's think back to our rational root theorem. And we did a video on that, and that helps us to know what our possible solutions are, and I'll link that in the cards right now. So if I'm looking at this, our possible solutions. Okay, and remember the rational root theorem tells us that we can identify these possible solutions from our constant term and from our leading coefficient. So our constant term, all of its factors are going to be the numerators of our possible solutions, and the leading coefficient is going to be our denominator. So the rational root theorem is awesome to use when we have a leading coefficient of 1, because then all of our denominators are 1 and they just go away. So whenever we're listing our possible solutions, we want to do this positive and negative. So we're going to basically just write out the factors of 36, or negative 36. So positive or negative 1, positive or negative 2, positive or negative 3, positive or negative 4, positive negative 6, positive or negative 9, positive or negative 12, positive or negative 18, and positive or negative 36. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 18 possible solutions here. And these are just the real solutions. We might also have some complex solutions as well. And so let's start off just with 1. And remember, we said we can use the synthetic division process to help us figure out if a solution is an actual solution if we get a remainder of 0. So let's start with 1. So we're going to see if 1 is a solution. So to do that, we're going to do our synthetic division process. And remember, this is for all of our coefficients. So 1, 3, 9, 23. Notice I'm going from my x squared term to my constant term, so we need to put a 0 in here for our linear term, or our term that would just have an x. And then lastly, negative 36. Okay? So now for synthetic division, we always bring down our first number, and we're going to multiply the diagonals and add the verticals. So 1 times 1 is 1, 3 plus 1 is 4, 4 times 1 is 4. 9 times 4 would be, not 9 times 4, 9 plus 4 would be 13. 13 times 1, 13. 23 plus 13 is 36. 36 times 1 is 36. 0 plus 36 is 36. 36 times 1 is 36. And negative 36 plus 36 is 0. So the key there is we got a remainder of a 0, which means 1 is a solution. And so remember, if we write this as a factor, we would write this as x minus 1, because once we set that equal to 0, that's where the x equals 1 comes from. So now what I want to do is let's check and see if 1 is a repeated solution. So what we can do is just continue on our synthetic division process and not include our remainder there of a 0. So let's put 1 here again, and let's see if we get 0 again for our remainder. And if we do, we know that 1 is a repeated root, and we want to take note of that because even if it's repeated, we want to count it because that's what the fundamental theorem of algebra states. So now we're going to bring down our 1 again. 1 times 1 is 1. This would be 5, 5, 18, 18, 54, 54, and 90. So did we end up with a remainder of 0? No, we did not. So what that tells us is 1 is a solution, but just one time. It's not a repeated solution. So what I'm going to do is go ahead and erase what we did right here. And now I'm going to go ahead and check another solution. How about negative 1? Let's see if negative 1 is a solution. Okay, so we bring down our 1. This would be negative 1. This would be 3, negative 3, 10, negative 10, 26, negative 26, and 10. So we didn't end up with a remainder of a 0, so negative 1 is also not a solution. So let's take away these, and now let's try 2. So we put 2 right here. So this would be 2, 6, 6 times 2 would be 12, 25. Notice how large my numbers are getting, right? And so obviously we're not going to end up with a remainder of a 0 here. So 2 would not be a solution. All right, let's try negative 2. So now we've got negative 2 here, positive 2, negative 4, 9, negative 18, positive 18, negative 36, and 0. So we found another solution. So we're going to write this as x plus 2 as our factor. And now let's see if negative 2 is a repeated solution. So now let's continue on our synthetic division here, just to our 18. And let's put negative 2 there again and see if it is a repeated root or a repeated solution. So negative 2, 0, 0, 9, negative 18, and look what happens. We get 0 again. So negative 2 happens to be a repeated solution. So now we can just put an exponent right there and say it's x plus 2 quantity squared. And now we could continue on, but notice what we have as our remainder. This is our remainder, this is our linear term, this is our constant term, our linear term, and our quadratic. So now we're left with x squared plus 9 as a factor, and so we can write that up here. Okay, and so we now can set all of these 3 factors equal to 0 to find our possible solutions. Okay, so x minus 1 equals 0, so we get x is equal to 1. X plus 2 quantity squared equals 0. So we take the square root of both sides. We get x plus 2 equals 0. So x is equal to negative 2. And we get x squared plus 9 equals 0. So we subtract our 9. And notice what happens here. We're taking the square root of a negative. So we can't do that in the real number system, but we can do that in our complex number system. So we can say x is equal to, and this would be the square root of 9 times the square root of negative 1. And we know that the square root of 9 is 3, and the square root of negative 1 is I. And remember, we did the square root, so this is plus or minus. Okay, so plus or minus. So now let's write out all of our solutions and see if we do have 5 of them. So we have negative 2, and remember that was a repeated solution, so we're going to list negative 2 twice. We have 1, we have negative 3i, and we have positive 3i. Okay, so look at our solutions. 1, 2, 3, 4, 5. That's what the fundamental theorem of algebra said that we should have because our degree of our polynomial was 5. And that is how you can use the fundamental theorem of algebra.